Hey, it's time to start up. How's your day going? And can you hear me reasonably well? Okay. So glad to hear that. Let's think. How about I'll start with mentioning a couple administrative things, nothing major, just to make sure we're all on the same page. And then if you have any questions about administrative things first things first, then subject matter questions related to class from Tuesday, then diving in, sort of a deep dive on ANOVA, literally how it works, the logic behind it, as well as some equations. Then a discussion of under which circumstances should you definitely use ANOVA or perhaps not use ANOVA. Okay. And then what if you do an analysis of variance and find out that indeed one of your groups is noticeably differing from the others in terms of the average? Which group is it? Following up on that and trying to figure out which group is different is probably an important thing to do. It's sort of the natural question that follows up, believing the alternative hypothesis that not all the means are the same. And so we'll sort of end there, and then the lab will correspond to you checking to make sure that the method will work in one particular data set case. And then maybe for a different data set, you'll also do the post hoc analysis. In other words, let's figure out which means differ from which other means. Any administrative questions before I sort of dive in and just show you something on my screen? Okay. So then I'm gonna grab that screen, hopefully. Oh,
I actually
question.
had a small one.
Yeah,
Uh,
Harrison.
no worries if so, but is that homework still due on Monday, even though we have the day off?
Yeah, good point. I'll change that to be due on Tuesday.
Awesome.
My life, and probably many of you have the exact same situation in your lives. It seems like I can't tell the difference between a weekday and a weekend. And so I just totally forgot about the holiday. It's in the syllabus as, yeah, no new content for the Monday class. Well, we don't meet on Monday, but for a couple weeks from now, when we sort of have the Tuesday class actually follows a Monday schedule, so we won't be meeting. So yeah, thank you for reminding me of that. I'll have that adjusted to Tuesday. And so the lab will be due on Tuesday as well as the homework at about the same time period. Okay. Thank you for mentioning that. Okay, so I'm just going to sort of show you the thing that I look at every day when I click my way into Canvas. But yeah, and thank you for mentioning this. A couple of you alerted my attention to the fact that there was something a bit awkward in terms of the link that I was provided and just copied and pasted into Canvas. That changed somehow. And so I've believe I've updated this. These should be live links to a Zoom room, if you will, that Monday through Thursday, 4 to 7. If you click your way into that Zoom room, they should be able to help you with the basic stat concepts. And that carries us through at least chapter 3. Now, we will find that some of the later concepts as well will be appropriate for that group of individuals. But my recommendation is if you were to request an appointment, you could click your way into that link and you will be able to say, yeah, here are times when are good for me. And then you could then expect someone to sort of get back to you with when are times that they could set up an appointment with you. And I think that what they like to do is collect individuals from one whole class together. So if there's 2 or 3 of you who say, hey, I definitely want to sort of go explore these ideas additionally, and office hours aren't convenient times, sort of signing up as a collection there means you're going up to the top of the priority list in terms of them attaching a tutor to you all. But I clicked my way into week 2 and stuff happens. Yeah, that's from last time. I'm currently videotaping this in theory, and I'll be right after class is over. Once it lets me know the link is live, I create the video link there. Those homework, yeah, due Tuesday of next week. Thank you. And the lab for the day today, if I were clicking my way into that, you could see clicking. Okay, well, it's there. Okay, good. So you'll probably be using the docs version. That's what most students seem to be using. But if you like PDF, that's fine too. And then 2 different data sets, antibiotics, and then the diet and lifespan. Did any of you download those already? Okay, Maggie, you did, and they all worked? Okay, good, because it's always embarrassing, but inevitably it will happen at some point in time that I'll upload something and then the way I did it was not quite right, and I need to fix that. So I can like fix that as we talk if need be. So before class, if any of you have the opportunity to download things related to the lab, that's always good. And if there are problems, letting me know right away will help me get that fixed before too late. Okay,
I
but
actually
yeah,
downloaded
please.
them from the zip file, not necessarily like that specific link. So I
Okay,
don't know if
but
that's
yeah,
different or not.
those are the same data sets. They are in the zip file, but also a direct link here. But I was mostly concerned about, could you get into the lab as well?
Yeah, I downloaded the doc.
Okay, perfect. So we're happy.
Professor, just one
Yeah.
more administrative thing. I believe
Sure.
we actually don't have class next Tuesday. I think next Tuesday follows a Monday schedule.
Okay, well,
But
that's fine. If that's the case, that's easier for me. Oh, yeah, that's right. So I'm going to verify that, but that strikes me as familiar. And boy, that makes life a lot easier. But then it also means probably I need to adjust the syllabus to correspond to that. So things will be bumped a little bit as appropriate. So let me actually do this now live, because why not? And let's see where the syllabus is, because if I got that wrong, boy, that would suck. So it says February 16 is the date that we're doing that in the syllabus. So if you check Harrison and verify your belief, I'm going to do that also. And we'll try and resolve that by the end of this hour. If you do check and verify that you're right, let me know. If you check and verify that I put in the syllabus correctly, that it's then that we are following the Monday schedule on February 16th. That'd be great to know. But I'm not going to do that one. I'll address that one later if you don't have a chance to check it between now and the end of the lecture hour. Okay. Okay. Thanks.
Yeah, I think I just pulled it up on Cal Poly's site, and I believe you have them switched. So, but double check me, and we can.
Yeah, well, I will definitely fix that then, and that has some issues that I probably would want to think through carefully rather than on the fly. So let me think that one through, and I'll verify that before too long. Okay, so let's just say we stopped last time when we were looking at I guess we were using a different data set, the diet and lifespan data that you'll use the lab for in the lab today. To illustrate ANOVA, last time you used the handicap and discrimination against the handicap data set for the lab. I'm just going to go ahead and reproduce the analysis that you guys had done, but I'm going to emphasize things a little bit differently so we can get towards partitioning the amount of variability in total across the whole of the data set. So fit y by x is my friend. The scores may be differing between handicap groups. We'll find out if that's the case. This first graph here shown does nicely say, how do the data vary away from the average score? This horizontal line just below 5 is the average score across all of the data points. And perhaps from group to group to group, there's a difference in the mean, and the total amount of variability could be broken down in terms of, for example, with the crutch group, rather than variability of each data point relative to the average, it could be compared to the average for the group. So I'm going to display then the group means. Indeed, each data point, instead of saying it's well, 7.4 is how much above the average of about 4.9. So that's 2.5 above average. Well, this same data point at 7.4 is compared to the average across all of them at 5.9. It's only 1.5 above average for its group, but its group average is 1 unit above the average for the scores given out. The notion that we really have here is the total amount of variability, vertical spread of the data points, regardless of which group they're in, can be broken into how much spread is there between the group averages and how much spread is there within each group. Again, we'll call that partitioning variability. There's a total amount of variability, SSY is SSY is the total amount of variability. That's the way our book refers to it. Okay. There are other names that we could give that. SS total, okay, is one that I will sometimes use. And then there's a variability between the treatment groups. And then there's error of the data points relative to the group means. Let's say I'm going to partition this ANOVA table. Again, we said last time it's a collection of calculations that are some checkpoints, if you will, or an Excel-like way of thinking, doing a whole bunch of calculations all in one table and displaying things that relate to ultimately your answer, the F ratio, and then the corresponding p-value here. That F ratio is your test statistic. How do we partition that? Well, we're going to say there's a column I'll call degrees of freedom. For degrees of freedom, you should think it's related to pieces of information. Okay, either the number of data points that you have or the number of groups that you have, if you will. How many pieces of information do you have? We'll talk on the next slide about that guy. There's a sums of squares. That's a measure of variability of the data values compared to an average. Okay, what that average is to be determined. This column called mean square, it's an intermediate step towards getting that F ratio. And literally the F ratio is a number that tends to be about 1 if the null hypothesis of all the means being the same is true. And it tends to be larger than 1 if the alternative hypothesis is true. And the p-value is just a way of saying how well do our data match the null hypothesis, or if you will, how likely is it that our F ratio would be as large as what we did get, or perhaps even larger, if the null were true. So to introduce you to the notation that we'll be using, and many of you have seen these terms before, so I'm not going to sort of slow down and dwell on it. I'm just going to say these are symbols that make sense to the bulk of us. The new ones would be like K, the number of groups that you have, the number of treatment groups you have. So with the 5 handicap groups, K would be 5. If you have 6 different diets you give to the mice, K would be 6. N sub I is the number of data points from group I. And so if you have 14 data points from each of 5 groups, N1 would be 14 because there's 14 data points in the first group. N2 would be 14, N3 would be 14. N is the sum of all of the NIs adding across all the groups. How many data points do you have in total? Well, I'm thinking 5 groups at 14 per group, that's 70. N would be 70. Yij is the jth data point from group I. Okay, so for example, Y22 is the second group. Y2 is the second group, second data point. There you go, 2.5. Y42 would be the 4th day group and then the second data point in group 4. So it's a 2.1. Okay, 4th group being the hearing loss group, the second data point. So the ij subscript tells us which group, first off with I, and then the second thing that we get out of that is the data point number within the group. Y bar I, it's the average of group I. That's easy. I'm sorry, SI, that should not read squared. SI is the standard deviation of group I. If it's SI squared, it should read the variance of group I. Y bar bar is adding up across all groups, and then all data points within each group, okay? And then dividing through by the total number of data points, the values. In other words, average them all, regardless of what group they're in. Find the average of everybody. Okay, I'm gonna just take a screenshot of that. And if you want, I can put that online later. It's sort of a good reference to have. It's probably something that you already have somewhere, but if you don't, certainly having it written down somewhere would be good. So I'll put the screenshot online. Okay, degrees of freedom, bits of information. In total, we say 69 degrees of freedom. It's the number of data points minus 1. Now, why the minus 1? I don't want to go into that for now. I'll just say minus 1. Okay. How many degrees of freedom across the 5 different handicap groups? Well, there's 5 groups minus 1. That's 4 different, if you will, degrees of freedom. Okay. Number of groups minus 1 is the number of, if you will, parameters I need to estimate. Okay. The degrees of freedom attributable to error, or DF error, is, well, the number which, when you add it to the degrees of freedom between the groups, gets you the total degrees of freedom. It's literally n minus 1 minus k minus 1 within a parenthesis. That's going to be n minus k. So we have just n minus k degrees of freedom for error. And that degrees of freedom for error plays sort of a huge role later in the term. Okay, so any questions about how to subtract 1 from k? Or n from k? If I tell you k and I tell you n, could you figure it out? What if I tell you that there's 5 data points per group and there's 6 groups? Could you figure out all these terms? 30 data points in total. Okay, so 29 degrees of freedom total, 6 groups. So k is 6, k minus 1 is 5. 29 minus 5 is 24. Yeah, you could figure them all out. So if I tell you the number of data points per group and the number of groups that you have, you're home free for figuring out these degrees of freedom. Second term, set of terms. The way we measure variability. And again, like before, 2 of these added up forms the total. So you can see numerically 30.5 plus 173.3 is 203.8. Yeah, that checks out. This is sort of easy to actually prove this to be true, that the first 2 lines added together gives us that third line. But I'm going to say, if life gives you group means, y bars, and ends, okay, and then you could figure out then, of course, y bar bar, the weighted average across the group means, you could figure out SST treatment very quickly. If, again, I tell you y bars for each group, and then the sample size n for each group, you can calculate the weighted average, okay, y bar bar very easily, and then figure out this sum of the squared differences. And shoot, squared differences, that's sort of like a standard deviation almost. It measures the spread. How differently spread apart are the group means from the grand mean? This is a number that tends to be small if the group means are all close together. It tends to be large if they're far apart. SS error measures how closely the individual data points are to their group average. Okay, another way of phrasing that, although, you know, this is true, this is more easily calculatable. If I tell you n and s for each group, I could take those individual variances, okay, multiply by n minus 1 and add them up. So if life gives you standard deviations and sample sizes, SS error could be calculated very easily. This last one, always a pain in the ass to do by hand. Okay. In fact, it's always a pain in the ass to do these things by hand. But R.A. Fisher, who invented the method, had to do these all by hand, so he had to figure out some shortcuts. I'm going to tell you a classic problem for an example exam would be something like this. If I were to give you no information about the degrees of freedom column, but I tell you the number of data points from each group, and if I tell you maybe S from each group, and if I tell you SS total, could you figure out all of the terms in these first two columns? Something to jot down as an example problem to work through. Next slide. Oh, actually, do any of you want to ask about any of these things for clarification purposes first? Okay, next slide. Again, we're moving towards our ultimate F ratio. Next step is this third column over. It's a mean square, and it's literally take the sum of squares, divide through by the corresponding degrees of freedom. 30.5 over 4 is about 7.5. Well, a little bit more than that, 7.63. 173 over 65, that's harder to do by hand, but if you had a calculator, 173.32 divided by 65, yeah, 2.666, we're good. So these numbers, mean square, let me tell you one thing about mean square error. Mean square error, no matter what, in every circumstance, is an estimate of the assumed common variance for each group. Let me say that one more time by just putting the words in a different order. If there is a common variance, a common standard deviation squared in each group, then mean square error is my estimate of that unknown number, period. That's it. Mean square error estimates that unknown common variance. If the null hypothesis is true, it turns out via methods that are a little beyond the scope of this class, but are covered in Stat 523. If you're going to go on and emphasize designing experiments further in your curriculum, further in your studies, you'll learn the proof of why mean square between the treatment groups also tends to be about equal to that unknown common sigma square value, if the null is true. And so if the null is true, we've got the ratio of two things that tend to be equal. And so the F ratio tends to be about 1 if the null is true. If, on the other hand, the null hypothesis is false, as we talked about last time, sum of squares between the treatment groups will tend to be large. Thus, the mean square between the treatment groups will tend to be large. Thus, the F ratio will tend to be large. Was our F ratio here large? 0.03 is the p-value that allows me to say our F ratio 2.86 was so large that it would only happen in 3 out of 100 studies if really handicap is unrelated to the scores that these people give out. So in other words, if there is no bias towards or against any particular handicap group, then in only 3 out of 100 studies would my F ratio be 2.86 or larger. At the end of the day, I'm going to conclude that there is a statistically significant or noticeable difference across the groups. Any questions about this example?
Yeah.
Yeah.
So if there is a common variance, is it the mean square error is the estimate or just the mean square?
Mean square error
Okay.
will be an estimate of that common variance common to all of the different groups. And if the null hypothesis is true, that all the group means are identical to each other, then mean square across the handicap groups will also be an estimate of that unknown yet assumed common variance across all the groups. And so that's why the F ratio tends to be about 1 if the null is true, but larger than 1 if it's not. Does that address your issue, Harrison?
Yeah, thank you.
Anyone else want to follow up on that? I think it's a really good question to pause on if you want.
If you had more data points, would it affect F ratio?
Great question. If I had more data points, no matter what, mean square error will still be about 2.666. It's not going to tend to climb or drop systematically, right? Degrees of freedom associated with the treatment groups will also still be 4 if I had more data points per group. But let's go back a slide. If I have more data points, N will be growing. Supposing instead of 14 data points per group, I had 28. I would have 28 in locations where formerly I had 14. The new sum of squares treatment would be about double what the old one was, yeah? And so our mean square would be double what the old one was. So the F ratio will be about double what the old one was. So the F ratio will be climbing. My p-value should thus also drop. Let me rephrase that. More data is good. Now, some of you are the sort that would have watched Saturday Night Live reruns. And I remember back in the 90s, and some of you are thinking you weren't even born then, but whatever. You may have seen it, the Frankenstein, Tarzan, and Tonto sketch, where one of them will say "fire bad," because Frankenstein, Tarzan, and Tonto, they use like these short sentences. My version of that for statistics is data good. More data allows us to be more likely to see a difference if there really is one. So Ali, the issue really is this: if there are subtle differences between different population means, more data tends to raise the F ratio, causing me to be more easily able to spot the difference between the population means. Because although the sample means still remain about the same, more data allows me to say, aha, now I am sure of the pattern that only I had seen as a hint earlier on. Okay. I'd like to sort of say we're always gonna be, January 19th follows. Yeah, thank you. Thank you, Marissa. So I'm gonna rewrite the whole syllabus overnight, not dramatically, but it's gonna basically be, we're not meeting next Tuesday is what it is. And so I have until next Thursday to sort of adjust the syllabus. Damn it. Okay, so I want to switch gears and say it will take us a little while to feel completely comfortable with every aspect of the ANOVA table, but fortunately, we're going to use the ANOVA table all term long, and you'll get real comfortable with it by the time it's really mattering.
Can I ask a short question, please, before
Sure.
we move on? So,
Yeah.
Ali was talking about how if the degrees of freedom get larger, then our F ratio gets higher because the numerator in that ratio grows. So inversely, does that mean if our F ratio is less than 1, that we don't have enough data to make a statement either way? How do we interpret a really low F ratio?
Well, a low F ratio will mean the p-value is above 0.05, which we would say, I'm not yet convinced that there's a difference between any of the population means. Now, you asked about what if the F ratio is less than 1. That says, not only am I not convinced, I don't even see a reason for pursuing this further, unless in theory there really ought to be a difference across the group means. A very small F ratio, and you suggested less than 1, so I'll go roll with that version of the example. A very small F ratio says, even if there was a difference, it's really tiny. There's no reason to look further unless there's a real important consideration or distinction to be made if the populations were different. But we have no suggestion that that might even be true in the data just yet.
Right, because you mentioned earlier that a ratio exactly equal to 1 means that there's no difference.
Yeah.
So I guess that, let's say it's something really, really tiny, like 0.0001. Would
That's
that
an
give
F-
us any, as an F ratio, would that give us
Yeah.
additional information beyond saying that there's no difference like we have with a ratio of 1?
No,
No,
that
it's not,
just
it's basically the
that just
same.
that just says that our sample means are almost darn near exactly identical.
Okay,
That's about all
Okay.
it says. Yeah.
okay, thank you.
Okay. So I'm gonna skip the right-hand triangle geometry thing, but not completely. I'm just gonna skip some of it at the very tail end of chapter 2, and we'll hit some other parts of it later. I'm just gonna say the Pythagorean theorem works nicely, right? A squared plus b squared is c squared, if c is that right angle. In our book, our authors suggest that if you view the distance from the model where there is only one mean to a model where there's one mean for each handicap group, okay, there's a certain amount of explainability that you're able to get. The squared length is sort of like SS between the treatment groups. What's left is unexplainable and, if you will, orthogonal at a right angle too. Okay. At a right angle too. So the squared length corresponds to SS error. And so the squared length here, a squared plus b squared equals c squared. Yeah, that's the total amount of variability. From the data to the mean can be broken down to total amount of variability between the data and then the group means, and then the group means relative to one common mean. Okay, some students are like, yeah, I got it. And others are like, well, show me this 3 or 4 more times. I'll just say our author keeps relying on geometry here. And if you didn't get it the first time, most of you will get it the second or perhaps the third time. And if you don't get it by the third time, everything is still easy to grab onto. It's just that some students so much benefit from the geometry, it's worth mentioning. Okay. Same thing works for degrees of freedom, but that's what I skipped. Okay, so let's just say we have a collection of assumptions that are necessary for any statistical procedure to be deemed reasonable. Okay. The assumptions for the ANOVA procedure are that there is one common standard deviation to each and every one of the groups, no matter what treatment we apply. Whether it's a handicap of an amputation or no apparent handicap or wheelchair, there's the same spread, same standard deviation in the scores that we will observe if we were to simply sample enough people and force them to watch those videotapes. Equality of standard deviation. And the second assumption or requirement is normality. In each and every group, you need to have a normal population of possible scores. We saw some of the scores, we saw 14 exactly. Across all of them, it has to be a normal shape. Now, I'm going to move over here off to the side to make an aside comment. Well, maybe I can move off to this side. Okay, I'm going to skip moving to the side. An aside comment is the following. Our book overstresses this. All intro stat books overstress this. Studies based on simulations in the last 20 years or so pretty clearly point out that if you have normality, we don't so much care about equality of standard deviation. The p-values are still reasonable. Or if you have equality of standard deviation, we don't care so much about normality. Again, the p-values are reasonable to believe. In real life, we stress only as statisticians if you have a lack of normality and different standard deviations. And if that's the case, in chapter 8, we're going to show you a solution to a problem in that context in some cases. Okay, so normality and equality of spread, how could we even check them? The lab asks you to do this. I'm going to say you're going to use the Levene procedure to check for equality of spread. So inside our analysis, if we were to turn on the mean / ANOVA, you can see the p-value like you did last time, 0.0301. If you were, however, to have said, aha, check for unequal variances, it tests literally to find out if you have a lack of equality of spread. And down at the bottom, we see a variety of choices given to us: O'Brien, Brown, Forsyth, Levene, Bartlett, Welch. I'm going to recommend the Levene procedure. Okay. The reason I recommend Levene is that it's sort of like that multi-tool that you have. Or maybe you don't have a multi-tool, but instead of just a pocket knife with blades and that's it, a multi-tool also has like pliers on it, and it's got like a screwdriver, and it's got multiple types of things attached to it. It's like a Swiss Army knife, if you will. Okay, this multi-tool procedure Levene is never the best tool to use, but it's always close to good enough. Okay, so the null hypothesis for the Levene procedure is that all of the population means are identical. If I have a p-value of 0.93, I have no reason to reject the null hypothesis of equality of spread. So check. We've got equality of spread. Actually, I don't know it to be true, but if it were true, I saw data that match what I would have expected to see. There's no reason to doubt an assumption of equal spread. Similarly, the Shapiro-Wilks procedure, okay, Anderson-Darling's also fine. There's also Kolmogorov-Smirnov as well. But Shapiro-Wilk as a procedure, it flows sort of naturally from a quantile plot or just adding a normal curve to a histogram of values. Okay, what we're going to recommend doing, okay, to check for normality is to save what I will term as residuals, and then check equality of spread for the residuals. Now look at that graph here. Maybe I'll turn off the mean diamonds and we'll see a similarity. If I were to redo my analysis after having saved the residuals. So let me show you how to save the residuals. What is a residual? A residual, as we'll learn later this term, is how different is a data point from what the model would suggest it should equal. If our model allows each group to have its own group mean, the residual is how far above average for your group you are as an individual. So if I under save those residuals, I've got a new column here. Notice that its new column is scores centered by handicap. This -3 says this individual data point, the 1.9, was 3 units below the average for its group. So if I were to show you now under Analyze, let's go with the same procedure, Analyze these residuals separately relative to the fit y by x scores were relative to handicap. I see the exact same graph, except for now, notice that the amputees, it looks as though, well, shoot, these are the same dots, right? Yeah, 1 low, then 2, then sort of a gap, then 1, then a gap of 3, 1 low, then 2, then a gap, then 1, then a gap, then 3. Yeah, these values here originally were stretched out a little bit. And they've been centered here at where the mean was. So relative to this green line, how far above the green line are the data points? This guy here is 2.9 above the group average. Every group has thus been shuffled so that way it's right at the same height, the height of 0. Now I can take all of these data points as a collection and say, let's, instead of looking at normality in each and every group, let's look at normality across all of the groups simultaneously. They're all centered at the same location. If I were to analyze the distribution now of those residuals, I click OK. Where did it appear? Oh, here it is. When you have multiple screens, things appear in sometimes the not preferred place. And I like to sort of stack these up so I can see it very nicely. Does that look normal, perfectly normal in every way? It looks a little skewed, yeah? I'm going to go ahead and add a normal curve to it. So I'm going to add a continuous fit of a normal. So the line that was just drawn in here in green, okay, corresponds to the perfectly shaped normal curve. I could also choose to display a normal quantile plot for these data. And these data relative to the normal quantile plot says normal seems reasonable to believe. If you remember from your earlier stat class, normal quantile plots, if you have the data points following a straight line, you'd say normal is reasonable to believe. Once I've added in the green normal fit, comparing the data points to that green normal fit, I could do that with the fitted normal curve over here. I'm going to tell you it averages 0. Here's the standard deviation. Okay. I could turn on now the goodness of fit test, and literally Shapiro-Wilk says null hypothesis of normality would not be rejected. There's no reason to doubt normality. Okay, a lot of steps, but the steps are in the lab, so it's okay to go through it quickly. The real idea is, though, check the distribution. Okay, how do you do it? You add a continuous fit of a normal curve, then add the goodness of fit test, okay, and look at the Shapiro-Wilk p-value. Again, null hypothesis normal, you're looking for a departure from normality. If you don't see a departure from normality, there's a reason to believe that normal is a-okay. As an assumption, it's not noticeably silly. So I feel pretty good about this ANOVA, the ANOVA that I did earlier. And that ANOVA said at least one of the groups is different from one of the others, yeah? On average, at least one of the means is different from the others. Which group is different? If the null hypothesis is rejected, and I've got 5 groups, I'm thinking if group 1 were to be compared to group 2, and 1 to 3, 1 to 4, 1 to 5, 2 to 3, 2 to 4, 2 to 5, 3 to 4, 3 to 5, 4 to 5, I've got 10 separate values. Literally, if I told you mu1 minus mu2, mu1 minus mu3, etc., all 10 of these pairs of values, you could put them in order from lowest to highest means, yeah? If you know the lowest mean, you know the lowest mean. You know the next lowest mean, you put them in order, lowest to highest. You could put them in order. So my thought is, let's come up with a collection of confidence intervals for each and every pair of differences. Mu3 minus mu4, I'll get you a confidence interval for that. Mu1 minus mu6, a confidence interval for that one as well. Every pair. But the problem is, again, if there's a 5% rate of error in a confidence interval, if I only capture the truth 95% of the time, there's a 5% rate of error. And across 10 separate procedures, my error rate overall could be climbing. So let's think through in a thought experiment. What if I do 10 procedures that instead of being 95% sure, what if I do 10 procedures that are 99% sure? Would the overall rate of error drop to lower? It should. It should. So we're going to, if you will, use 10 separate confidence intervals, each of which has a higher level of confidence. And if we balance it out just right, we'll have overall a family-wide error rate of 5%. So in other words, across all 10 confidence intervals that I'm going to produce, I want to be 95% sure that all of them cover their corresponding truths. Okay, so it's done by simply ratcheting up the confidence level of an individual confidence procedure for each and every one of the individuals until we have the overall error rate at 10%. And that's where, unfortunately, we end up in a bit of a pickle because there's so many different theoretically optimal ways of doing it. Okay, so I'm going to mention just 3. Okay, Bonferroni. I'm going to say if you use the brown textbook, no, not the brown textbook, it's now blue. If you were to use the Ramsey Schaefer textbook, it goes into a great explanation for the logic behind the procedure. If you have the Stat 218 textbook that's commonly used, again, in chapter 12, towards the end, chapter 12, section 9, it does explain the logic behind this procedure. So the logic behind Bonferroni is the way you want to do the reading. Just know that Tukey as a method, or the Tukey-Cramer method, is the one which is, again, like your multi-tool approach. Okay, it's never the best, but it's always one of the top 3 relative to the other alternatives. If I could tell you a particular situation, theoretically, the best approach is student Newman-Kuhl's, you'd say, okay, I want to use that one. Okay, or Sue's method. But for each and every theoretical situation where there is one optimal, Tukey is always pretty darn close to it, with slightly wider confidence intervals than the optimal method. But unless you know that you're in one of those optimal situations, okay, it's always as good as you're gonna get, or so darn close, we just recommend using the Tukey procedure. So let me show you how to do it, and then we'll talk about how to get there, okay? That's where we're gonna end up, but I'll show you how to turn on the Tukey procedure. Under, you can see, compare means. Let's compare means using the Tukey procedure, okay, Tukey HSD, for honest significant difference. Okay, so the Tukey procedure, comparing every pair. And we could talk in office hours if you want to about Dunnett as a method, or the student Newman-Kuhl's or stepwise Newman-Kuhl's, or if you will, Sue's comparison to the best, or Fisher's, if you will. I just say use Tukey. So the Tukey procedure, what it does for me is it has extra width, so I'm gonna make it wider here. And it shows this. I never really pay attention to that graph, and I always just bump right down to where the Tukey output is. And it says, if you want to be 95% sure to be right all the time for every one of the confidence intervals, you have an overall error rate of 0.05, 5%. So instead of going up and down 2 standard errors, go up and down 2.80582 standard errors. That's the Tukey procedure. It just tells you the t value to use. Now, if you have the ability to just do that by hand, great. But even better for you, down at the bottom, there's this thing called the ordered differences report. Our textbook authors say the largest possible difference is Crutch minus Hearing, with a difference of 1.87. Second largest difference, third, fourth, all the way down through the smallest possible difference. And they're ordered positively. So Crutch group is larger than the Hearing group by 1.87 in our sample. Crutch larger than amputee by 1.5. amputee larger than hearing by 0.38. So we put them in order from largest to smallest differences. And there's, of course, a standard error. And then with our Q value, we go up and down Q standard errors to get a confidence interval for every difference. So I'm 95% sure that every one of these confidence intervals, that the crutch mean mu for crutch minus mu for hearing loss, is in the 0.14 to 3.6 range. And also that mu crutch minus mu amputee is in the negative 0.24 to positive 3.2 range. And all of the others, including the amputee, mu amputee minus mu hearing, is in the negative 1.35 to 2.11 range. I'm 95% sure that all 10 of these confidence intervals contain the 10 corresponding population mean differences. Some folks will quickly just notice over here, look, it's in red. Red or orange indicates that's a noticeable or statistically significant difference. You could also say this confidence interval for mu crutch minus mu hearing is indeed entirely positive. Mu crutch minus mu amputee is at least 0.14. So it's certainly positive. I shouldn't say certainly, it's almost certainly positive. So where you see positive differences, only positive differences, you'll have a p-value below 0.05 that says that's a noticeable difference between those two groups. Let's try crutch compared to amputee. Mu crutch minus mu amputee is 95% sure to be in the negative 2.24 to positive 3.2 range. In other words, mu crutch minus mu amputee, mu crutch, the average crutch score might be as much as 3.22 higher than the average score given to the individual with the amputation. But it could be the case that the crutch score could be as much as 0.24 lower. So in that case, I'd say I can't tell you which group is higher in terms of the average. This thing called this connecting letters report is a SAS style version of output. JMP is written by this company called SAS in North Carolina. They say, let's put letters next to each group. So that way, if you have the same letter, you are not noticeably different from others in your group. So crutch and wheelchair and non and amputee, they're all labeled A. I can't say there's a difference between any of those. Wheelchair, non-amputee hearing, they're all B. There's no noticeable difference between any of those either. That connecting letters report usually, okay, is something that you could present in a different way, but connecting letters report is a way SAS chooses to do that. So the number of groups that you have that you're comparing plus the confidence level gives you your Q star, the order differences report pops out at you, and then identifying groups as not noticeably different versus clearly different. My approach is to say, just simplify the picture. This is a little bit more common than a connecting letters report. Just list them in order, lowest to highest. H, handicap, H, hearing loss, amputee, no apparent handicap, wheelchair, crutch. Put them in order from lowest to highest mean. Underline groups that are not noticeably different from each other. Hearing loss and wheelchair, no one in between is noticeably different. An amputee through crutch, none of them are noticeably different. So let me just close by saying, someone always wants to say similar to. Do not say that. You cannot say that amputee is similar to wheelchair. You can say they're not noticeably different. Here's an analogy I like to use to try and explain this. Do you ever have those two friends where if you invite one to a social function, everyone's happy and you all get along just fine? Or you could invite the other one and everyone's happy and everyone gets along just fine, but you don't dare invite both of them simultaneously to the same party. A couple of you are nodding like, yeah, I got that in my life. Yeah, here, the hearing loss group and the crutch group, they do not get along. They are clearly different. They are not in the same room. The others, they're flexible. They're not noticeably different from hearing loss or wheelchair or crutch or amputee. An amputee, no apparent handicap wheelchair, they're no different from crutch, but crutch and hearing loss, clearly there's a difference there. Okay, a lot of content. Okay, that's fine. I can deal with that. But I already know this stuff. You guys, however, usually benefit from doing the labs to sort of solidify that understanding. How about a couple questions if you have some? I noticed that no one interrupted me, so you might have a question now before I put you in some groups.
Yeah, going back to the Shapiro-Wilks
Yeah.
test.
Yep.
So is that pretty much that's pretty much, how do I say this? Because we're looking at the visualization of the data and then using the Shapiro to kind of reinforce what we see. So for example, if the p-value for the Shapiro-Wilk was below 0.05, then the distribution would not be normal?
Yes.
Okay.
It would be noticeably differing from normal. You didn't see an example here, but you might in the lab.
Okay.
And you would see the corresponding quantile plot will be curved. The histogram will be clearly skewed. Shapiro-Wilks will be below 0.05. You'd say, oh, look, not normal. There's a problem.
And would we like log transform that or do anything to make it normal, possibly?
I will say in a later chapter, that's the approach that we'd want to take. And this term, I'm going to want to put that in chapter 8. Fall term, there's an extra full class session, maybe 2, depending on which day of the class, which day of the week the class meets. And so fall term, we consider that earlier, but you're right. In some cases, if you had a skewed right collection of samples, maybe if you take a square root or a log of each and every value before you do your analysis, it's not wrong, and it may allow you to then use the procedure. You would then just be saying that, let's go with the log because you suggested it, Jack. If I say that the average of the log of the data points is different across the groups, that's another way of saying they're centered at a different location. Just the geometric mean would be different across the groups rather than the arithmetic mean is different across them. But still gets after the underlying question, are the groups different or not?
Okay, thank you.
Anyone else?
Going back to the, what did we do? The last thing that we did?
Yeah.
Where we tried to find the confidence intervals for all of these different differences.
Yeah.
So in what we're saying is that in 95% of experiments, our mean would be within all of these different confidence intervals. The difference in means for each of these values would be within these 2 confidence intervals for
Yes.
all of them.
Yes. So let me say that again. There is a mu for crutch group. The average score, should everyone be asked, hey, how qualified is this person? And there is a mu for the hearing loss group. What would be the average score given if they watch the hearing loss videotape? We only have samples of 14 from each group. Okay. But we are 95% sure that this confidence interval here and all of them will all contain the corresponding difference of population means. I'm 95% sure that this whole family of confidence intervals correctly captures the corresponding numbers we're attempting to estimate, the 10 separate differences of population means.
So if we wanted to prove something specifically that you'd rather have crutches than a hearing aid if you're going to go into an interview, then you'd want to do something like a t-test to measure that, because you might be able to tighten that confidence interval by doing that.
So if you only cared about comparing 2 of these 5 groups, and that's it, then a confidence interval should be 95% for that one comparison of interest. And that would be entirely appropriate to do.
Okay.
And as you note, rather than going up and down 2.8 standard errors, it's probably going up and down only about 2 standard errors. It's going to be a narrower confidence interval, more precision, if you will, which we like.
Okay, thank you.
Okay, so what I'm going to do is stop the recording here and then pop you into your lab groups to work on. And again, there will still be some issues. I was not able to correct all of the auto magic assignment to groups, but you're getting used to knowing where you're supposed to be, and you'll just request which room you're supposed to be in. And if you don't remember it, we'll figure it out. Okay. And if you do end up in the wrong room, raise your hand and I'll eventually get you into the right place. I'm pretty sure there will still be a couple errors that are the same as last time because I wasn't able to correct them all, but you know, we'll do our best as we go and we'll be happy in the long run. So I'm stopping the recording.